So in Blender, have you ever wanted to know how big a mesh is? Maybe you've got several meshes and you want to organize them by how big they are, or you want to delete ones which are too large. Well, there is now a way that you can do so in geometry nodes, and I'll just show you how to do it. Let's start with this nice torus object here. So you want to go to geometry nodes, zoom out a bit, create a new geometry node for it. So the basic idea behind this method is we want to take each face, and it needs to be triangulated. With each face we are going to build what's called a tetrahedra, so a four-sided shape, and it's going to have one face which is the object face, and then it's going to have a fourth point which is going to be the center, and you build a four-sided shape around that, and you can work out the volume from there. We're not going to actually build a mesh of those shapes, but we're going to do the maths as if we were. So you might think that if you just add up all the tetrahedra, then you're not actually going to get the volume because some parts are, inside and they're going to be empty. They're not going to contribute to the actual size. Well, the good thing is you can actually have assigned volume for the tetrahedra, so you can have them negative and positive, and then when you combine them all together at the end you are left with just the object's volume. Anyway, let's get started on the actual geometry nodes. So the first step, very simple. I've set space to search, so let's find it. So anyway, the first step is to triangulate. Okay. Now you see it's a bunch of triangles. So the idea is that we want to add up all of these. So what we want to do is we want to use the attribute statistic node to find the sum of all of these volumes for all the faces. So I'll just show you how to do that. So attribute statistic, annoyingly you have to scroll down quite a bit. Okay, pop that in. We get the geometry. Let's split it like that so we've still got the object. Right, let's give it an output so we can actually see the values that's being generated. So we want to take the sum value, but we want to turn that into something we can read. So value to string, take the sum, plug it into there, and then the string we want to go into an info node. Plug it in there. And now you can see over here we have a value and a little info thing. If we increase the number of decimal points, you see it adds it there. Right now it's just reading nothing. We want to change that to the faces. And now we want to build how it reads the tetrahedra. This is a neat bit of vector maths, which I won't go through in detail, but you can read up if you're that way inclined. Okay, let's move these over and get a bit of space. So what we want to do is we want to sample all of the corners of each face, which we can do like this. So I want to sample the index. So we want to select face corner because we want it to go through each face and find the respective corner. So let's take position. Because the fourth point of the tetrahedra is going to be the origin, we can simply take the position as the relevant vector. If you wanted to measure from another point, you'd have to subtract that from the position and it gets more complicated. But if we just keep it as the origin, then we can purely take the position as the relevant vector. Okay, let's change this to vector to sample that. Okay, now to tell it which index we want to probably, because this is taking index 0 of the entire thing, which we don't want, we need to take the corners of face, take the corner index and plug it in. Now what we want to do is repeat this more times, and change this to sort index 1, this to sort index 2. Let's connect all these up to the same source of geometry. There we go. And now here comes the vector maths part, which I'm not going to try and explain here, but yes, you can look it up. So, vector math. Take that, and we want to take the cross product. And take 2 of these values in and plug it into that. Duplicate that and change it to the dot product. Plug that in there, plug that in there. And again, for complicated reasons, we now need to divide this value by 6. So divide by 6. And now, if we plug that into the attribute, we now have value there. Cool. And let's just double check it. I'm using the 3D print add-on. I can go there, and the volume of this is, yes, basically the same. I'm not quite sure why there's any error there, but anyway. Okay, so now that we have this value, let's see if we can do anything with it. So how about let's make another object that has, we want them to have exactly the same volume to them. Okay, let's say add a primitive cube. Something nice and simple that we know exactly the volume of. Cool. Let's join these together so we have them in the same scene. And let's transform this and move it over to the side somewhere. How far is it? Where is it? There it is. Let's move it all the way out so we can actually see it. Change that back to 1. Okay, and now because we know that the cube already has a volume of 1, what we can do is we can take the volume value, and if we just put it through a math node first, and this is to basically find the cube root of it so that we can scale it properly. So power exponent 1 divided by 3, take the sum, put it into the base, and then value to the scale. See, we've now got a cube. Okay, let's just double check that they are linked. So over here, let's just add another transform geometry, plug it in, and then we can change the scale. See how it changes? Cool. And let's see if we can have it update in real time. Okay, so I'll go into edit mode, and let's make sure proportional editing is on. And then if we start moving and dragging it around, see it's starting to change the size of the cube that was generated. Cool. Okay, for fun, let's make it so that 2 objects that are, well, slightly more complicated than the cube have the same volume. So let's clean all this up a bit. Let's get rid of that, and let's turn all of this, all of this into a group, and then the sum. Okay, cool. Let's call this the mesh volume. Mesh volume node. Cool. Let's make a completely separate object and bring that in. So let's make let's make it a sphere, but can make it a bit more interesting. Just move stuff around. Okay, cool, weird shape. So we bring it into this object info. So that's relative. Set the icosphere. Let's put it through the same mesh to volume mode, and let's take the sum and see if it updates. Yep, see it's changed. Right, let's add in a transform geometry. And hit the right button. Cool. Bring that into there. Let's just hide it so we're only looking at the one. And to make them match and have the same volume, we want to take the ratio of this. So maths, divide. So we take the one we want it to match with, put it up to there, and then take the sum of the volume we want to scale. And now instead of plugging this straight into the scale, we can plug this into the exponent. Ta-da. And cool. Let's double check this. So we can actually duplicate that. And we can duplicate these and plug it in. And now you see there's two values. In fact, we can do that here as well. See? Again, not quite sure where the errors are coming in, but I'm assuming that's just a rounding error. So this method is quite similar to things like finding the center of mass, or finding the center of the volume of the object as well, which I'll go into in another video. This tool I've built, and it's part of the lattice generator that I have on sale, and it actually tells you how much material the lattice is going to use, so you can very precisely control exactly how much you want your 3D printed object to weigh. Cool. I think I might put this and a few other tools together as its own add-on, which I'll put online at some point in the near future. Cool.